Okay, so let's dive into these related rates and get to some more examples that will help hopefully allow you to see how these are done in a more regular way. So we have an example up here that's a little better than that stupid rectangle example. You drop a pebble in the water and it makes circular ripples. The ripples are moving out. We know how fast the ripples are moving. How's the area changing? You could also make this a problem where there's an oil spill in the ocean. Oh wait, that's not really so much as a theoretical problem. That's happened. And they need to track exactly how fast that oil is spreading and where. And there's a lot of variables involved in that, but it's the same idea. So the one word I didn't put in is we're going to assume these are circles, circular ripples. And we're looking for how the area is changing. So what type of equation would we be looking for here? Think about it. Could it be the area of those circles? What's the area formula? Pi r squared. So that takes care of the first step up here. I do want to bring your attention to one more thing in the problem, and it's not something you necessarily have to do to solve it, but it's good to recognize what does this 4 inches per second represent? 4 inches per second. Sometimes it's really useful to mark down the known values that they have, the data, and to recognize what it represents. So I like to sort of list my assets here. And if you guess that 4 inches per second actually represents how fast the radius is changing, that's great, and it is a positive 4. So, simply put, we've got a few more things to do. Plug in any constants. Does the radius stay the same throughout this? Is it the same length, or does it keep getting bigger? Does the area stay the same, or does it keep getting bigger? If there's no constants, skip over that. We still don't need to worry about the auxiliary equation quite yet, but it's coming soon. And then finally, we're going to derive this with respect to time and plug in the numbers. And I was in such a hurry to write this problem that I apparently forgot one really important part. When you derive this, you do have the radius there. I never told you what the original radius was. At any given moment, this could be different. So if the radius is only 1 inch right at the beginning, the area is not going to be changing as much. If you get to a point where the radius is, say, 20 inches and still growing, then the change in the area is going to be much larger. That's why these are related rates. It's not a linear thing. It's not that one specific rate here is going to be the same as the area. So we can plug in different things, whatever the radius is. I apologize for not writing one down. Let's just say it is 20. And since that's 20 inches, it's always good to also include units in your final answer. This is in inches, that's in inches per second. And it should come as no surprise that the answer for area over time is going to be inches squared per second. Your units should match up with what you're saying. If it's an area, it'll be inches squared. If it's a radius, it'll just be inches. And if it was a volume, it'd be inches cubed. Speaking of volumes, let's try one more example here. Now we have a water cooler. You're dropping some water out. We've got some dimensions, 40 centimeters for the diameter, 60 centimeters for the height. When you open it up, there's 3 cubic centimeters of water pouring out of it per second. How fast is the water level changing? Now, when we ask for how fast the water level is changing, what exactly is it that we're looking for? Probably the change in height over time. Okay, so let's go through. We need to determine an equation. What do we know? What are we looking for? Take a second. Yeah, that's good enough. Okay, what we should be looking for, well, we have the volume of this cylinder. We have some dimensions of it, maybe a volume formula. For some of these, you might need to look up the formulas. That's okay. The next thing we do is we plug in any constants. As the water gets lower and lower in this tank, does the height change? If so, it's not a constant. Does the radius change? I think it is. So if the radius does not change, if it's a constant, plug that number in right now. This makes the rest a lot easier. Now we can take the derivative and plug in. See here, the derivative, we actually knew the change in the volume. We can solve for dH/dt. Please note, in this one, it doesn't even matter the height to find the rate at which it's changing.